Okay, second problem. We're going to start with a function g of x equals 3 over 4 plus x in quantity squared, little g of x. Then we're going to find capital G of x, the antiderivative of that function. Um, we're going to just choose that constant there to be 0. So we're going to find the antiderivative, set that constant equal to 0. It's an antiderivative. We're going to find the power series representation of that capital G of x, the antiderivative function. And then if we take the derivative of that function, we'll get back to the original function, little g of x. And if you think about the constant, let's say you chose a constant of 10 for your capital G of x, and then you took the derivative, well, the derivative of 10 would be 0, so that constant will drop back out regardless. So anti-differentiate, set that constant equal to 0, find the power series representation, and then differentiate it to find the power series representation of the original function. Okay, and I'll go ahead and open up the whiteboard. Stop sharing board. So our original function, little g of x, is 1 over, sorry, little g of x, original function, is 3 over 4 plus x quantity squared. Okay. And what we're going to do with that guy is find its antiderivative. So capital G of x is the antiderivative of little g of x dx. Okay, so we're integrating 3 times, this is 4 plus x in quantity to the negative 2 dx. 3 is a constant. We're going to take the 4 plus x, increase the power by 1 to get to the negative 1, and multiply in front by the reciprocal of that power, which will just be negative 1. So we'll have 3 times negative 1 times 4 plus x to the negative 1, and then plus a constant. So that's negative 3 times 4 plus x to the negative 1 plus that constant. We're going to choose that constant to be 0 because capital G is the set of all the family of functions with all the constants, one of those constants being 0. So that certainly is an antiderivative of little g of x. And then I want to rewrite this as negative 3 in front times 1 over 4 plus x. And the next part asks us to find the power series representation of that. So to do that, we need to remember that we want to get it in the right form. So I'll just draw a line here. Hang on to the next step. We're going to factor the 4 out. So I'm going to get negative 3 over 4 times the fraction 1 over the quantity. So factor the 4 out, I get a 1. So plus x over 4, but we need it to be a minus. So I'm going to leave the negative 3/4 in front and rewrite this as 1 over the quantity 1 minus little negative x over 4. When I multiply this through, the minus and negative becomes a plus, times it by 4. Downstairs, I get 4 plus x, and then the negative 3 would be on top, which gets us all the way back up to here. So we can always check these sort of simplification steps here as we go. Once we have that, the power series representation is pretty straightforward because negative 3/4 is a constant, pull it out in front, times the sum from n equals 0 to infinity of negative x over 4 to the n. And that's converging, I'll just do it up here, on the absolute value of negative x over 4 less than 1. I'm going to ignore the negative and go x over 4. I can do that because it's the absolute value. So x over 4 is between negative 1 and 1, and therefore x is between negative 4 and 4. That's going to be my interval of convergence for all the functions. Okay. So I've got my capital G of x, which was the antiderivative of little g of x. And now to find the power series representation of little g of x, we want to take the derivative of capital G of x. And we're going to do it by taking term by term. So little g of x is g prime of x, which is -3/4. And now here it's a little bit weird. When n is 0, this first term, the n equals 0 term, this would be 1, because -x/4 to the 0 is 1. The derivative of 1 is 0. So I'm going to write that, I'm going to pull that first term out, and then I'm going to have the sum from n equals 1 to infinity of whatever's left. And what's left is when I take the derivative of this thing, I get n times x/4, -x/4. It's so tiny, sorry. To the n minus 1, and then chain rule, I got to multiply here by the derivative of -x/4, which is -1/4. Okay, do a little bit of simplification work here. I guess I can still leave this -3/4 out in front. Not worried about that. 0 is going away. I'm going to still start at 1 for a minute, from 1 to infinity. So I've got my n. I've got a -1/4 and another to the n minus 1 and another -1/4 here. So I've got -1/4 to the n, and then times x to the n minus 1. So I pulled that -1/4 out because I had another one over here. I still have a -1/4 in front that I could also bring in, but I don't care. We can leave it out there. It's fine. But I need to get my index to start back at 0. So we're going to decrease our index by 1. Decrease by 1, which will increase all of the n's over here by 1. So that'll be an n plus 1. That'll be an n plus 1. And this will become the power n. So we'll get -3/4 times the sum from n equals 0 to infinity. This guy becomes increased by 1, n plus 1, times -1/4. Increase that guy by 1, n plus 1 to the n plus 1, and then times x, increase that by 1, just becomes x to the n. And then the last part of the problem is asking for the interval of convergence, which we already found. It's from -4 to 4. So we'll just say at the bottom here, on the interval from -4 to 4. Okay, and that ends that second problem. The problems themselves will be posted along with their solutions if you want to look at those. Good practice. And then real quick, just to recap that process overall, let me just close this for a second. And if I go back, sorry, if I go back to the original problem where we're looking at the original function, little g of x, we don't know how to do the power series of that. But if we take its antiderivative, capital G of x, we get something that we do know how to find the power series of. We find the power series representation of it, and then we take the derivative of it to get back to the original function and find its power series representation. All right, that's it. Good work. Sharing.